Welcome back. This is part 2 of our first lecture. In this part, what I'm going to do is to introduce you to big data and machine learning, to these two concepts, okay? And especially my view on these topics. That will be a more statistical perspective into machine learning methods. Okay? So what's the agenda for this part? I'm going to start like defining what's big data in economics and finance, what's data science, and then what's machine learning and types of machine learning methods. So let's start with one fact that nowadays we have data everywhere. We have data on GPSs, on your mobile phone, cameras, supermarkets, newspapers, comes with Excel files and the stock exchange, airplanes send signals to satellites in real time. So we have a large amount of data. We are producing in a very fast way a large amount of data, and we have to analyze this data. We have to extract information from these extremely large data sets. Okay? So just to give you an idea, this is from 2020, from this page, Data Never Sleeps. So it's basically how much data is created every minute. So here you can see, for instance, how many Zoom participants you have in a minute, like more than 200,000, or how many people engage with content in Reddit, like more than 700,000. So stories posted in Instagram, new users in Twitter. So you see the number here in this picture. So you see that these numbers are pretty high, meaning that all of these we are generating data. We have information. So for instance, every minute Amazon ships more than 6,000 packages. So all this, each package has information attached to it. Who bought it? What are the contents of the package? To where it is going to be shipped? So when was it bought? What was the price? So all these are relevant information for us to analyze. So we need this information to extract some knowledge from this data. Okay? So just for you to have an idea how lively is the analytics market, so the global big data and business analytics market is expected to grow from $192.24 billion in 2019 to more than 400 billion by the end of 2025. Okay? This is an estimate from Report Linker. Okay? So the annual growth rate will be around 15%. This is huge. And if you imagine that the cost of an analytic tool in 2019 was more expensive than in 2020, and for certainly it would be much more expensive than in 2025, this growth in terms of spending is also a much bigger growth in terms of new tools and usage that we are going to see. For instance, 10 years ago, using Amazon Cloud to run a program, a computer program, was much more expensive than it is today. So nowadays we can have codes running over the cloud in multiple core computers at a very low cost. So we can run many more programs. We can use many more cores nowadays than we could do like a couple of years ago. So this increase shows that the area and the industry is growing at a very speedy way, and it's still alive with all COVID-19 crisis. Even though this is an area it's growing a lot, people need data, people are producing data and analyzing this data and getting knowledge, reliable knowledge out of it is really, really important. Okay? So basically, big data is characterized by a large volume of different types of data, and this amount of data increases very fast, and it exceeds beyond reach of commonly used hardware and software. So you have to think about how to store this data, how to process this data. It's not something that it's easy to do or traditional solutions can handle it. It's something that we need like special computers, like to store the data and to analyze all this amount of information. Okay? And it challenges like the basic statistics, the basic econometrics. So when you learn econometrics 101, you deal with like reasonable sized data sets. Here we are talking about extremely large data sets, not only in terms of observations, but also in terms of variables, of attributes that we save. So imagine an airplane that's sending all the kinds of information to a satellite at real time. So if you have like a 12-hour flight, 10-hour flight, during all this period, the airplane is sending all the information about all the avionics. So this is a huge data set. Or a financial institution that has like thousands or hundreds of thousands of clients, and this institution saves basically all the characteristics of the clients and all the investments made by the clients. So this is also a huge information. Okay? So what we want to do, we want to process this data, estimate a statistical model that's be reliable statistical model, and to test hypotheses, to make decisions, basically to help policymakers, to help managers to make better decisions. So in the end of the day, what we want is to make better decisions, to make more informed decisions. Okay? So we say that big data has the 4 V's. So it's volume, velocity, because we have new data almost every millisecond, variety, different source of data, and veracity, which is important because we have to know if the data that we are getting is a reliable data or not. So checking veracity, checking the quality of the data is really important. Okay, so here we have a picture of that kind of summarizes these 4 V's. Okay, and there is a joke also that the V's of big data are also big because people start creating new V's. It's more so you have like viability, visualization, virality, volatility, validity, venue. So you see that the whole definitions, because apart from the joke, the thing is that the data rich. We are talking about very rich data sets. We are beyond the old Excel spreadsheet, like with a limited number of rows and lines. Now we are talking about really vast data that can go from numbers to text to audio to video. So now I'm recording a video. There's information in this video. So this video has a lot of data in it. That's what I'm saying, what you are looking at, or the duration of the video. There's a lot of information here that's important and that can be used. Okay, and continue with the joke. There is this estimate that in basically this year, we are going to provide like 120 Vs for big data. Okay, that's just a joke to relax. Okay, so basically, in economics, what we can say about big data, we know that like in genomics and astrophysics, in many areas, okay, big data is natural when we have like satellite reads, sensor reads, but in economics, okay, the fact is that in economics, the data sets are also expanding. Okay, there's a very good paper by these two authors here that's called The Economics in the Age of Big Data. Now it's a kind of old paper because it's 2014, okay? But still they are envisioning how important is big data in economics, okay? So they basically say that the quality and quantity of data on economic activity are expanding rapidly. Empirical research increasingly relies on newly available large-scale administrative data or private sector data that often is obtained through collaboration with private firms. Because now you're beyond that public data that you can download from the internet, and you have like huge data sets from companies, from firms, or from the government. Okay, so just to give you an idea of examples, okay, in terms of macrofinance, we have a very nice real-time databases provided by the Federal Reserve at St. Louis. So that's called the FRED MD, and now they have the FRED QD. So it's for monthly and quarterly data. So it's basically a set of more than 100 macrofinance variables that are recorded in real time. So they save every vintage of the data. So take, for example, industrial production. So industrial production is released in one day, but it can suffer revisions. So basically, in that website, you have the original release data, but you also have all the vintages, all the revisions of the data for inflation, for industrial production, for all of these data, all these variables. So it's a very rich database for anyone interested in macroeconomics and finance, and also looking at the interaction between these two fields. We also now have transaction data available, transaction data from the stock market, from the stock exchange, from trades and quotes database. So you have like all data at the tick level. So you have everything from all the equities trade, for instance, at the New York Stock Exchange or NASDAQ. So you have this data that's basically tick by tick, and you have prices, you have the bid price, you have the ask prices. So it's a very rich data set. We have Twitter, Facebook, and also social media data that you can put your hands on it and analyze this kind of data. We have text data, news data. So just to give you an example of two providers, Factiva and Ravenpack, they provide, for instance, all the front pages of the Wall Street Journal since the first edition of the journal. So this is very rich because you can start analyzing text. So there's a big field now in economics, econometric statistics, and machine learning that's called text as data. How can you use text to extract information? So you transform text into numbers, and you put these numbers into, you feed a model, you feed the statistical model with these numbers, and to, for instance, let's say, forecast stock returns. Okay, there are many applications. It's a very lively field of research. So just to give you an example of the amount of data we have nowadays in economics and finance. Okay, so here is an example from the same paper. the authors compare the share, okay, of administrative data and private data from firms over the total empirical papers in one of the main economics journal, the American Economic Review. And basically the message here is just to see that, like in the early 2000s, most of the data sets were public data sets, okay? Where people were analyzing data that you can get from the internet that are totally, and this changed over the years, and now about only 50% of the empirical work in AER is concerned with public data. The rest, like administrative or private data from firms. Okay? So this shows that the availability of these new and rich data sets is increasing. Okay? All right. All that said, okay, which kind of data we are talking about? So there are basically two sorts of data sets: structured versus unstructured data. Okay? So what's structured data? Is what most of you are used to. Is the Excel spreadsheet. So highly organized information that you can have like a traditional row database structures. You have like fixed fields, and this is basically what you can put in a table and analyze by traditional methods. Okay, and so this sort of data is simple to store, carry, analyze. Okay, but you have to associate the data with a certain field, and you have to label the type of the data, if it's numeric, if it's date, if it's currency, or if it's alphanumeric. Okay, and as a result, is often restricted by character number or specific terminology. Unstructured data, everything else, sky's the limit. So there's no organization or how this data are organized. So examples, text files, but text files can come in different ways. You can have a poem, you can have the full book, you can have a news, you can have the news highlight, or there are many ways where you can see that. It can be text in an image, a text in a picture. Okay, so you also have images. So you have a photo of someone and you want to know if that person is happy or sad, or you want to do face recognition, and so you have data there, and you have to transform this image into something that can be analyzed by an algorithm or a model. So you have web pages, web scraping, extracting data from the web, extracting prices of products over web searches. Social media, you want to know if a certain tweet is a positive tweet or is a negative tweet. You want to look at emails to determine if it's a valid email or is a spam or is a fraud. Okay? So all this kind of data are labeled as unstructured data. And usually what we do with machine learning models is to take this unstructured data and make it structured. Transform this data in a way it can be analyzed by an algorithm, by a statistical model, a machine learning model. So let me give you an example. It's by this paper by Baker, Bloom, and Davis, which appeared in the Quarterly Journal of Economics in 2016. What these authors created, it was an economic policy uncertainty index. So they want to create a time series, an index, that indicates how uncertain is the economy about economic policy, how uncertain the agents, the individuals, are about economic policy. How they do that? They have like three components, but nowadays only one of these three components is the most important, and is the number one. They take here the newspaper coverage of economic uncertainty. They look at the news of the most important newspapers in the US, and they analyze all the news to see if they are kind of how they are related to economic policy uncertainty. Okay. They also have other two ingredients: the level of uncertainty regarding the path that the federal tax code will take in the future, and also disagreement among economic forecasters. Okay, these two here they are less important now, and they are mostly concerned about that one here, because they started this index with the US, and now you can basically download the Economic Policy Uncertainty, or EPU, from several countries all over the world, right? And so basically they move from unstructured to structured data. Okay? So what they do, the first component, this component number one here, what they do is they construct and normalize the index of search results from 10 large newspapers. So here you can see the newspaper. So basically they count words, number of words that are related to economic policy uncertainty. Okay? And they construct an index with these counts. So this picture here gives you an example of the index. That's the index for the US. That's the version published in the original paper. This series is updated very frequently. You can check the web page here, and where you see this updated index not only for the US but for other countries. So you see here, when the index peaks, it's related to more uncertainty, to more unstable periods. So it peaks on 9/11, Second Gulf War, debt ceiling dispute, banking crisis, Black Monday, first Gulf War, Clinton election. So over elections, the Obama election. So you see, it's kind of, you can give an interpretation for that. So basically, there's kind of a magic going on here, because what you have newspapers, news, and you are transforming this vast amount of text, of unstructured data, into something that's really structured. It's a time series that you can plug in a model, in a forecasting model, in a macro model, in an asset pricing model. So if you want to have a variable that measures economic policy, you have it here. Okay? So it's a very nice example about how to move from one sort of data to another sort of data. Okay? A second example comes from a paper in Journal of Financial Economics by Moreira and Monella. It's the new implied VIX. So I don't know if everyone is familiar with VIX, but VIX is kind of a measure of volatility, computed from option prices. Okay, and what they want to know is what's the share of a news in the variation of the VIX. So they want to compute kind of a news implied VIX. How much of this volatility, of this uncertainty, is related to news? Okay. So what they do, they take a data set that dates back to 1890, and they collect the front page articles of the Wall Street Journal since 1890. Okay? And what they are going to do, they are going to count words. They are going to construct several counts of different words that will be based on a dictionary. We are going to see this paper many times during the course. I'm going to give you more details about this paper in the future. But they construct measures related to uncertainty, unexpected news. And what they do, they try to explain how much of the time evolution of the VIX can be explained by these news, by these variables that they construct. And they show the NVIX, their measure of news implied VIX, peaks during market crashes, times of policy-related uncertainty, world wars, and crises. Okay? And US post-war data, periods when NVIX is high are followed by periods of above-average stock returns, even after controlling for contemporaneous and forward-looking measures of stock market volatility. So it is a very interesting variable that was constructed completely from newspapers articles. Okay? And they also show that the news-based VIX is a key predictor of the equity premium. Okay? And what basically they do, they run a machine learning regression of VIX on these regressors based on text data. We will come back to this example later. Okay? And this news implied VIX can be downloaded from the author's webpage. So it's also free to use. Anyone interested in this data can download the data from the author's webpage. Okay? So this is an example here. So basically what they show, the black lines here is the actual VIX, but they only have VIX from very recently, right? So they estimate the VIX here in this period, that's the test period, the train period, in the red dots here is where they estimate the model. They test the fit here in the blue area, and what they do, they go backwards and they generate a series of the news implied VIX into the past. So they have they construct a series of this news implied VIX since 1890. Okay, so this is the whole series. So they use recent data to train a model, to estimate a model, and then they go backwards and they generate data to the beginning of the sample. Okay? It's a very nice application of machine learning, of unstructured data, and how to move from unstructured data to structured data. Okay? So continue here. What's big data? So there's this quote by Hal Varian, a very important economist. He's the chief economist of Google. He says that the sexy job in the next 10 years will be statisticians, because now we really do have essentially free and unambiguous data. So the complementary factors, the ability to understand that data and extract value from it. In my view, I would have said that the sexy job in the next 10 years will be the data science. I think it's even broader than statisticians, because not only we have to analyze the data, but we have to put the data in a way that statisticians can analyze. So what we are doing here in this course, we're going to take data ready to use. Okay? But there's a big share of the work that's like cleaning the data, transforming the data in a way that can be plugged into, we can feed a model, or where we can feed an algorithm to use this data. Okay, so this leads us to what is data science. What's related here? So we know big data is this vast amount of data that comes in very frequently. It's a large amount of data. It grows very fast, and where we can extract nice information. But how we can do that? Okay, how we are going to extract this information. Okay? And of course, also in these turbulent times, you may think, okay, so there are challenges and opportunities for big data and COVID-19. And of course, we are generating data, and it's very important for the control of the pandemic also to analyze COVID data and to take actions based on that. Of course, there are many privacy challenges here, but I'm listing some of the applications that we can do in light of this crisis. Okay, so far people are doing like strategic planning, tracking individuals, provision of advice to concern possibly infected individuals, and also forecasting. Myself, I am part of a group here in Brazil, for instance, that use machine learning methods to forecast the evolution of the disease in a country. So we have a machine learning model that can forecast very precisely how the disease is going to evolve in the very short term, in the very short run, like in the following couple of weeks. Okay? So this is a kind of an example. All right. So now we move to data science and machine learning. We learn what's big data, what are the challenges and opportunities, and now we have to move into the science of analyzing these big data sets. Okay? So what, in my view, what is data science? Data science, in fact, the union of different areas that starts here with database, creating the data. So where you start to learn what do you have in your data set, how you're going to store this data set, how you're going to process this data set. So this is a big part of the work that's constructing the database. So when I decide, oh, someone saved all the front page articles of Wall Street Journal. So this is saved somewhere in a certain format. What it is? It's an image, it's a PDF image. What is that? It's a text file. So, and then that's one part. And then I'm going there and I'm going to take this data and to process this data, I have to save it also in a specific format. So this database work is really important, okay? And then another component of data science is programming and optimization. We have to code. And it's not light coding, because we are creating new algorithms all the time, okay? We are merging different ideas, combining different algorithms. So we have to know programming and also optimization, because as you are going to see, to find a specific model or forecasting model or a model to make decisions about credit risk, for instance, you have to optimize a cost function. So you have to estimate this model by optimizing some criteria. So we need to know optimization. Okay? Of course, we must know statistics and prediction. Okay? But more than that, we have to know statistics in high dimensions. Because now is where we are. We are in high dimensions. So it's not the 20th century, 18th, 19th century statistics, is 21st century statistics. Okay? How to handle this really huge database where we can make reliable predictions, estimate precise models and make reliable predictions. Okay? And one topic that's becoming very, very important is causality. causal inference. And there's a big difference between prediction. It's usually different from causality. These are different concepts. Okay? Here you want to know what's going to happen with a certain variables if we observe something. Usually when we are doing causal inference, we want to know what's going to happen to a certain variable if we do something. So observation is different from doing something. Okay? So causality is also important. In this course, we are going to focus more here. We're going to give more attention to prediction, but we are not going to forget about causality. I'm going to talk also about causality. We are going to have lectures about that because this is also an important topic and is becoming more and more important also in finance and economics. Okay? So how machine learning compares to data science? I think machine learning is part of data science. It's the part where we have the data ready and we are going to start analyzing the data. So machine learning, for me, is the combination of optimization and programming, statistics and prediction, and causality and interpretation. The database part is left aside because we think, okay, we have this done, this job is done, and we can look into the modeling part, like let's construct models to extract information, extract knowledge from this data set. So what's machine learning? First of all, we have to ask ourselves, what do we want to learn? Okay? We want to learn something. Okay? Can be prediction mappings. You want a prediction function. You want to know how the market will behave tomorrow, what's going to be the inflation next month, when COVID will end. Okay? We want to make causal predictions. Okay? And if I do something, what's going to happen? So, for instance, if we decide to go into a strict lockdown, what's going to happen in terms of new cases and deaths by COVID-19? So you want to know the effects of a certain action. Okay? Or we may want to know some structural parameters. What is the discount rate of the economy? What is the price elasticity of a certain product? So we want to learn a parameter itself. Okay? So these are kind of objects that we may want to learn. Maybe you want to learn one of them. Maybe we are in a very ambitious problem that we want to learn all of them or have multiple goals in our problem. Okay? So from what do we want to learn? That's what we want, but we need something. Okay? What we need, data. That's an easy question. We are going to learn from data. We need the data. Okay? How do we want to learn? Okay, then we have some options. We can have like models, statistical models with very weak assumptions, or we can have statistical models with a set of much stronger assumptions. Why I'm making a difference between the two? Because it depends on what you want to learn. If you just want to make predictions, maybe you don't need a lot of assumptions about your data, about the nature of the problem that you're studying. But if you want to identify causal links among variables, then you may need to impose some restrictions on the nature of the problem. Otherwise, it will be impossible to identify these causal links. Okay? We have to choose a loss function. What's going to be the metric? How I rank between two answers to my question. I have, for instance, two models to predict inflation next month. Why model A is better than model B? So I need some metric. I need some criterion. So this is our loss function. Okay. So now, can we give a definition to machine learning? Okay, there is a traditional definition from Arthur Samuel, who was an AI pioneer. It's a definition from 1959. And basically it says that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. And this is a modification of the original sentence that says that programming computers to learn from experience should eventually eliminate the need for much of this detailed programming effort. If you look at this definition, especially the first one, it looks like that some magic will happen, okay? And from one day to the others, computers will be auto-programmed. They don't need a programmer anymore. And it's not really like that. We have to look into this in a different perspective, and I'm going to give you a definition of what I believe is machine learning. Okay, there are other definitions here from different sources. Basically, they say the same thing. Now, the machine learning is the science of getting computers to learn and act like humans do and improve their learning over time in an autonomous fashion by feeding them data and information in the form of observations and real-world interactions. So it's a pretty almost science fiction definition, right? Let me give you my take on this. So let's think about traditional program and imagine the task that you have to decide if you're going to give credit to someone or not. Okay? So basically, if you have to code a program in a traditional way to decide if you're going to give a loan to someone, what basically you do? You have some rules in your mind, you talk to experts to say, okay, no, to give that loan, that person must have a certain income, must have a certain age, live somewhere. So there are some rules. And basically what you're going to construct is a programming code that highlight these rules, to be like if then else type of rules. So if something is true, do something. Otherwise, do another act, take another action. Okay? So basically you have these large codes with all these rules. Okay? These if then else rules. And we code that, some new data comes of someone with specific features, you feed the computer with these features, and based on these rules, these if then else rules, you have an output that I'm going to give that person a loan or not. Okay? If you take the definition literally of machine learning, what happens is that you have data, you have a computer lying here on your screen, okay? Data is fed in the computer, magic happens, and what you have as an output is a program that will decide if someone will get the loan or not, but the computer was never programmed. See? Because machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So it looks like this. So it seems that's a kind of Harry Potter's approach. There's some magic and something happens. But that's not what Samuel was trying to say. It was not going to be programmed in the traditional way on if-then-else rules. So what's going to happen is that we have data, lots of data. We have a programmer that is going to create a code based on a mathematical statistical model that will be defined by an expert. Instead of the if then else rules, what this programmer will do is going to estimate a model that will take a statistical model to take the data, and it will create a rule, a mathematical rule, to say, depending on the features of the individuals, I'm going to say if the loan should be granted or not for that person. Okay? So the program itself is a statistical model with unknown parameters that will be learned from data. So this is machine learning. So when they say that the computer is not going to be programmed anymore, the computers are not going to be programmed anymore in the traditional way. They are going to be programmed in a new way, much more mathematical, much more statistical. So it will be a kind of very strong statistical background. Okay? So let me give you an example. So I want to know if this email here, this is my real email, if this email is a valid email. So if you are a traditional programmer, what you're going to say is if there are upper and lowercase letters or digits, and there is an @ followed by a valid domain, and there is not special characters and a lot of other rules, then this email is valid. Otherwise, this email is invalid. So that's the traditional programming before machine learning. In fact, nothing is learned. An expert or decided what are the rules that make an email address valid or not. Okay? The machine learning take is a little bit different. You have data on valid, invalid email address. So someone labeled a bunch of email addresses as a bad address or a good address. Okay, so we have like 3 examples here. So what you're going to do, you're going to feed this data into a program, into a model that will be a statistical model that will give you the probability of an email being valid. It will be a function of several inputs that we are going to have here. Oh, there is an @ there is a valid domain, there is not a valid domain, there are strange characters, there are not strange characters. Okay? And this model is a function of parameters. And you are going to optimize. Remember, we need optimization. We need statistics to construct the model. We need optimization because we have to solve the model, find the parameters. And then the output will be the estimated probability of a valid email. So this is machine learning. There's no magic. There is math. There is mathematics. There is mathematics. Sorry. Okay? So our goal here would be to construct these models. Okay? So this is my take on the problem. So my definition is that we are going to construct automated computer algorithms, methods, plus statistical models that will learn, that will discover hidden patterns from data. So we need data, we need an empirical question, that's what we want to learn. And depending on the empirical question, we are going to have different solutions, different models. Then we need a statistical model, a loss function, an optimization algorithm, and a way to evaluate these models. And then we are going to have the machine learning methods involving all these steps. So there is no magic. There's not like just pressing a button and the solution will appear in front of you. There's a lot of things going on in the background to have like algorithm, a computer algorithm that says that an email is valid or not. Okay? There's a lot of math behind the scenes. Okay? So machine learning can be also much more than just prediction models. As I mentioned, machine learning are usually used for prediction, but they are also being applied to causal inference. And remember, correlation association is different from causality. Okay? Clustering and text analytics are big areas also of research in machine learning. Okay? And machine learning are receiving a lot of attention in econometrics. First, because we have large data sets in economics nowadays, and nonlinear models are becoming popular. We have new tools to conduct inference. This is one thing that we are going to see in this course, how to conduct inference in this machine learning world, how to test hypotheses, okay? And we call statistical learning when machine learning methods are statistically sound. Okay? This course will be about statistical learning, okay? So sorry. This here will be our goal, statistical learning methods. So if we compare machine learning with econometrics, so the main goal in machine learning is prediction, classification, pattern recognition. Okay? Causality, it was not an issue, but this is changing fast. Okay? In econometrics, we are not only interested in prediction, but we want interpretation. We want to know why the model behaves the way it behaves. So this is important. So inference is important, and causal inference is a goal for decision making. But what I believe is that these two areas, machine learning and econometrics, if merged together, both can benefit. So, and this course here will be about these two things together. We are going to merge econometrics, statistics with machine learning. Okay? So there's a great matching. Of course, first the great matching. Why machine learning is popular nowadays is because we have big data, right? Machine learning has been around for many, many years, but why it's so popular now is because that's the way to go with these huge data sets. But it's three individual things. We have like machine learning, big data, and econometrics. So these three tools together can be extremely powerful. And is that what I want to convince you during these 12 weeks that we'll be together. Okay? All right. So what are the types of machine learning? Can we like segment this a little bit? Yes, we can. There are basically like three types of machine learning. One is what we call supervised learning here, which is the most traditional one, where you have data that are labeled, like so you have outputs and inputs, and you want to find a relation between inputs and outputs. Okay? So you have data on stock returns and characteristics of the firms, and you want to relate the returns with the characteristics. Okay? This is supervised learning. Or you have here unsupervised learning, and in this case you don't have the labels, you just have features, and you want, for instance, to group the data into different segments. For instance, you have a database of clients of a firm, of an institution, and you want to group these the clients that are similar according to some features altogether. Why you want to do that? Because, for instance, if you want to do direct marketing, so if there is a client who really doesn't like fixed income investments, you're not going to offer him or her an investment that's basically based on fixed income assets. Okay, so you want to segment your clients in a way that you can make more informed, better decisions. Okay? And finally, you have reinforcement learning, which is becoming very popular, and that's the idea behind, for instance, AI-based chess players or AlphaGo players, where you learn from the environment. It's about taking sequential decisions. You make a decision, okay? Something happens because of that decision. You evaluate what we call your reward, and you take a second decision, and you do that in a sequential way. And this is reinforcement learning. In this course, we are not going to talk about reinforcement learning. Unfortunately, we don't have time. We are going to mainly talk about supervised learning. This will be like 90% of the course. 10% of the course will be unsupervised learning. Of course, we could have like a 12-week course just on unsupervised learning, a 12-week course just on reinforcement learning. Unfortunately, we don't have time. Okay? So, can we put this in a mathematical way? So what's supervised learning? Supervised learning, you have basically an output variable, y, which will be a function of another variable, x, and this function here will be indexed by unknown parameters. We don't know these parameters, okay? This x can be small or big. Here, it's going to be big, okay? And you have a noise. What's the noise? Because we cannot explain, it's be impossible to have a perfect mapping between y and x, because there are many unknowns in the nature, okay? We don't measure all the x's that affects y, so there'll be a component here that's noise, that can be also due to measurement errors, okay? And then there is this mapping f, that can be either linear or non-linear, but we also don't know the mapping. So, what's the challenge here? We want to know this fellow here, and we want to know this fellow here. We want to learn the parameters, we want to learn the function. These are all linked together. Okay? Sometimes we specify a class of functions, and we would like to learn the parameters of this class of functions. And also, which is becoming more and more important, is to learn the features. Which variables we are going to include, because we may have hundreds of variables, hundreds of attributes, and it would be impossible to construct a model with these hundreds of attributes. So we have to restrict this to a smaller set of variables. So this will be a challenge that we are going to see how to deal with it here. Okay? We can also have binary classification, where the output is binary, 0, 1, give credit, do not give credit. And usually what we have is a function that will be an indicator function that will be equal to 1 if this argument here is greater than 0, for instance. Okay? And you want to, again, learn that function f. You want to select this variables, set of variables x. You want to learn these parameters. Okay? So, what is that? F of x. It can be the expected value of y given x. It can be a causal mapping. So we have to define what's this f of x. And we are going to discuss a lot about that during the course. Okay? So challenges, recover f and select x. Okay? So the mapping of f of x is frequently not known. So a solution, as I mentioned, is like to come up with an approximating class of models that we call hypotheses in the ML jargon. So it would be a class h of x given a set of parameters theta that we don't know theta. Okay? So theta is a vector of parameters that determines a particular model, a hypothesis in the jargon in this class. Okay? And we have data, a sample data, that will be observations of the random variables y and x. Okay? And we have to define what we call the empirical risk and the loss function. That will be, the empirical risk will be the average of that loss function. Okay? So we want to estimate theta that will define our model by optimizing, by minimizing the empirical risk. So here is where optimization kicks in. We have to solve this problem, which involves an optimization problem. That's what's called learning. Because we are going to learn what we are going to learn. We are going to learn that parameter theta. We are going to come up with an estimator. And then when we take this estimator to the data, we are going to have an estimate of that parameter that will give us the model that will be an approximation of this relationship between y and x. This is supervised learning. Unsupervised learning, no outputs, just inputs. And the goal is to find like interesting patterns in the data, and there's no desired outputs. You have just the features. So unconditional models, if you want to create clusters, missing value imputation, text analysis, dimension reduction are some examples. So these pictures, I think, tell everything. So you have a sample of different potatoes, different colors. They are all mixed together, and you want to cluster them. So each type of potato goes with potatoes of the same type. So everything's mixed, but then you separate them in different classes. That we want to do. Data be completely mixed, and we want to separate the data entries into different classes. Okay? So this is an example, a very clear graphical illustration of what is unsupervised learning. Reinforcement learning, as I mentioned, problems involving an agent that will interact with the environment, with nature, and which provides the agent numeric reward signals. So the goal is to learn how to take actions in order to maximize the reward. So you're playing chess, you want to make moves that will make you the winner of the game in the end. So there's this interaction between the agent and the environment, the nature. Okay? So there are many examples, like you can do like sequential treatments. There's some applications nowadays in trading that you use reinforcement learning to select among different trading strategies. Okay? So examples, so supervised learning, any paper with a regression function or a classification problem is an example of supervised learning. Okay? Unsupervised learning, I'm going to give you an example, is about text analysis. There's a technique that's called latent Dirichlet allocation, or LDA. That's basically a statistical model that allows set of observations to be explained by unobserved groups. So it's a topic model. So what are the observations? Are words collected from documents, and each document is a mixture of a small number of topics. So you say, okay, in this document I have like 4 possible topics, and you extract the text, and you are going to group words into these 4 possible topics. Okay? So in this paper by Hansen, McMahon, and Tong, they take the central bank communication, the Bank of England's inflation report, okay, and they analyze the report to see which kind of topics are more frequent in each report. And the topics are endogenously defined because they say, okay, let's say that we have like 4 topics in the report. I want the algorithm to browse the document and allocate different words for different topics. And here you have an example here where you see unemployment, employment, people, hour, time, rise, job is one topic. So basically it's related to unemployment. or labor market. Another topic is continuing demand growth. So it's basically about economic growth, demand growth. So these are examples of two topics that these authors found in the central bank communications. And they relate that to long-run interest rates movement. So it's a very interesting paper, again, that takes unstructured data, make it structured, conduct an unsupervised learning algorithms to come up with a topic model, and then use that to explain the dynamics of interest rates. So it's a very interesting paper. In terms of reinforcement learning, you can imagine, for instance, that valuation and hedging of financial derivatives are usually tackled using model-driven decision rules in a stochastic environment. So it's an optimal control problem if based on a well-chosen arbitrage-free martingale measure. So this paper by these four authors in Quantitative Finance last year, basically they provide a framework for hedging a portfolio of derivatives, of options, in the presence of market frictions. And their solution is based on reinforcement learning methods. They have a reward structure, and they construct the portfolio, they hedge a portfolio based on these sequential actions. So it's also a very interesting paper. Okay. So with that, I basically end the second block. We have an overview of the machine learning and big data models. Okay. The third block, the third part of this first lecture, we are going to open a little bit the box and look which sort of models we are talking about. Okay, so thank you very much and see you on the third video.